Okay, so in this video we will talk about rotation of rigid bodies, and we will emphasize on planar rigid bodies to start with. So rotation of planar rigid bodies. And this will the discussion on rotation of planar rigid bodies will lead us to the idea of the instantaneous center as well, which is a geometric concept that is very frequently used in solving problems in rigid body dynamics. So we'll get to that, but we'll start off with a very basic observation for rotation of a rigid body, and that observation is that, and it's a very elementary and an important observation, and that is any 2 points that are part of a rigid body of the same rigid body, and here we are focusing on planar rigid bodies. They rotate with respect to each other at the same angular speed omega at any given instant, where omega is the angular velocity of the rigid body. Itself. Okay, so this is a very basic observation, very basic concept that is important in solving problems in dynamics. The second concept that we are going to quickly discuss is the fact that small elementary displacements of rigid bodies that are undergoing both translations and rotations can be geometrically considered as a superposition of a translational motion and a rotational motion. And beyond that, you can consider that motion to be actually a pure rotation about a certain point, and that certain point is the instantaneous center. So to illustrate this idea, let us consider a rigid body, and I'm going to try to make the sketch as good as possible. It may not be very good, but I'll try. So I'm going to consider this rigid body, the same rigid body. Let's say this is the center of mass, and here the center of mass is here. So this is C and this is C prime, and this is a small displacement of the rigid body. Okay, not a significant but small elemental displacement of the rigid body. So now as the rigid body went from this location to this location, what has happened is that the center of mass has you can consider this motion to be a motion where the center of mass has translated and then the rigid body has rotated a little bit. You can see from the orientations that I have drawn these two in such a way that there is a small change in the orientation of the rigid body. So essentially, as the rigid body went from here to here, its motion was kind of like that. You know, the center moved and then the orientation also changed. So basically what you could have said is that the center moved from C to C prime, and it had so it translated from C to C prime without change in the orientation, and then the orientation changed by a small angle. Let's say that small angle is alpha. So you could say that the center translated by a distance d and then rotated by an angle alpha. Okay, and if I consider a point A, and let's say A had a velocity like this, and then in the rotated configuration, A is let's say A is here and its velocity is like this, then I can extend a line that is perpendicular to A, to the velocity of A, and similarly I can extend a line that is perpendicular to the velocity of, let's say this is A and this is A prime. So here we have VA prime and here we have VA, right? So I can extend a line perpendicular to VA prime and a line perpendicular to VA, and where they intersect, that is actually the instantaneous center about which we can consider the rigid body to have purely rotated. Okay, so this is a very important observation. So we make the following note, that we can consider the illustrated displacement of the planar rigid body in two ways. So we can consider that the displacement that has happened here, that we have shown here, we can consider this displacement in two different ways. One is C moved linearly to C prime without any change in orientation of rigid body, plus an angular displacement alpha about C prime. So we can consider the whole motion to be a composite, you see, of two things. One is the fact that C moved linearly to C prime without any change in orientation. So the rigid body was here, it just moved like this. So no change in orientation, it just moved without changing orientation, and C moved to C prime. And then followed by what happened was the rigid body then turned, okay, about C prime to orient itself in its final configuration. So we can consider the overall motion to be composed of these two, or we can say that alternately we can say that the rigid body underwent pure rotation about Q. Okay, and Q is the instantaneous center of rotation of the rigid body. Okay, so we can consider, so this is important because it tells us how, for example, you can consider the overall, any elemental motion of a rigid body can be considered, any elemental small motion of the rigid body can be considered as a superposition of a linear motion and a rotational motion. Alternately, it can be considered as a pure rotation. So no linear motion, but a pure rotation about a certain point. And that certain point is the point Q. And the point Q is such that it is perpendicular to, let's say I know the velocity of the point A, and we are going to discuss more about the characteristics of the instantaneous center of rotation. But essentially the way we have drawn it is, let's say there is a point A which has a velocity VA. So we drew a line that is perpendicular to VA, and we said that the instantaneous center will lie on that line. Okay, and then we took the point A prime and we drew its velocity, and we said that the instantaneous center will also lie along that line. We took a line perpendicular to the velocity, that is, and then we took the intersection of those two, and that's basically the instantaneous center. So we'll delve into this a little bit more, and we'll show what some of the techniques for finding the instantaneous center. But you can conceptually you can see that one way to consider the motion is a superposition of a translation and a rotation, and the other is to consider it as a pure rotation. Okay, so this is very important because this helps us in solving problems, formulating problems, and so on. A corollary of this is that when a rigid body, and we are still focusing on planar, so this discussion is for planar rigid bodies. When it goes to three-dimensional rigid bodies, the discussion gets a little bit complicated, but not too much, and we'll touch upon that in due course. So the corollary of this is when a rigid body has no rotational motion, so the motion is purely translational, the instantaneous center Q is at infinity, i.e. infinite radius of curvature pure rotation path. And that should make sense, because if there is no rotation, then the orientation is not changing, which means that if the velocity is at a certain direction at a certain instant, after an infinitesimal amount of time, the velocity still remains in the same direction. So when you draw this line perpendicular to the velocity vector, and when you draw the other line perpendicular to the new velocity vector after that infinitesimally small amount of time, those two lines are going to be parallel. And if they are parallel, then essentially you can say that their intersection is happening at infinity. So that is what we mean when we say that the instantaneous center is at infinity. Essentially it means that these lines don't intersect anymore. Okay, so that's a corollary of this idea of pure rotation of a rigid body about an instantaneous center. Now let's delve a little bit into the characteristics of this instantaneous center. So we'll make a few points. The first point that we'll make is that the instantaneous center of rotation of a planar rigid body is a point relative to which the velocities of all points on the rigid body are perpendicular. And we will illustrate this as we discuss forward, but essentially what we are saying is that with respect to the instantaneous center, every point on the rigid body of a planar rigid body that is undergoing a combination of translation and rotation, or rather undergoing pure rotation, instantaneous center is by definition the point about which the rigid body is undergoing pure rotation. So it is that point relative to which every point of the rigid body, their velocities are perpendicular, okay, to the line joining the instantaneous center to that point. Okay, so let's say from the instantaneous center I'm looking at a certain point on the rigid body. The velocity of that point is going to be perpendicular to that line joining the instantaneous center and that particular point of interest on the rigid body. We'll soon illustrate this. The second point that we'll make is that the instantaneous center can lie outside the rigid body. So it can be a hypothetical point which lies outside the physical confines of the dimensions of the rigid body. Okay. Also, it can change from one instant to the next. And this is why we refer to this point as the instantaneous center, because we are saying, we are giving a general definition of this point, where it is possible that the center about which the rigid body has this pure rotation changes from one instant to the next. And this is quite common. Okay. Next, let us delve a little bit into the direction of velocities with respect to the instantaneous center, as we have articulated over here in the first point on this page. So if I consider a rigid body, planar rigid body, and let's say there is a point A and it has a velocity VA, then the instantaneous center, and let's say that the rigid body does have rotations, then the instantaneous center is going to be on a line that is perpendicular to VA. Okay, so the instantaneous center is going to be somewhere on this line. Okay. Alright, so in fact let's call this A1 and this is VA1. Okay. Now let's say that there is another point here, A, and we call this A2, and it has a velocity like this, VA2, and it's the point A2 is on the same rigid body as A1. So the instantaneous center of rotation of the rigid body then is going to be, according to our definition, that the instantaneous center is always on a line that is perpendicular to the velocity at a certain point. So the instantaneous center is going to be on this line. Again, this line is perpendicular. So you see that if I know the velocities of 2 points on the same rigid body, I know their magnitude and directions, let's say, then by projecting, by using this geometric method where I draw a line that is perpendicular to the velocity of A1 and another line perpendicular to the velocity of A2, I can, by looking at the intersection, find out where the instantaneous center is. And this is the instantaneous center, and in fact this automatically means that if there is a point, let's say A3 here, alright, then I know that the velocity of the point A3 is now going to be perpendicular to the line joining the instantaneous center with A3. So let me draw a line. So this is a line that is now connecting C with A3, and I know, using the same principles, that the velocity at A3 is going to be perpendicular to this line. So that is VA3. Right? So you see that there is some utility of this geometric method. And to be more precise, if I can find out the instantaneous center, then I can use it to predict the direction in which a particular point on that same rigid body will have its velocity. Okay? So that's a very useful tool that can be used in many problems in dynamics. Now, since we are considering a planar rigid body, and you can see from the direction of the velocities that the rotation of the rigid body is in this direction, and we are considering planar, which means that the angular velocity vector is either going to be upwards from the page, perpendicular to the page, or downwards into the page but still perpendicular to the page. In this case, based on the direction of the velocities, it is quite evident that the angular velocity is pointed downwards perpendicular to the page. Now the basic relations between the velocities and the angular velocities is the following. You have Va1 is equal to omega cross R, and I'm going to say A1 with respect to C. Okay, and you can use the right-handed coordinate frame and the right-hand rule of finding the cross product of unit vectors to indeed see that the velocity of A1 is being predicted correctly, or the direction of velocity is being predicted correctly by this cross product, because omega is pointed downwards. So omega cross R A1 with respect to C is a vector going from C towards A1. So omega cross A1 is going to be in this direction, which you can see is in the direction of VA1. Okay. Similarly, we can say that VA2 is equal to omega cross R A2 with respect to C, and VA3 is equal to omega cross R A3 with respect to C. So one of the conclusions that we can draw from here is that that for a planar rigid body, the velocity at any point will be perpendicular. So this is the sign of perpendicular to R and omega. Okay, this is coming just from cross products, because VA1 is a cross product of omega and R. Similarly for VA2 and VA3. So clearly cross product is an operation that gives us a vector which is mutually perpendicular to these two. So clearly the velocity will be perpendicular to both omega and R. But from a geometric perspective, since R and omega are on the same plane, you see, sorry, not omega, since R and V are on the same plane, omega is perpendicular, but R and V turn out to be in the same plane. So the useful observation here is that therefore velocity will be perpendicular to the R vector. Okay, so for any point we can see that the velocity is going to be perpendicular to the R vector. And this is the basis of making the conclusion, or making the, or this is the basis of coming up with this geometric procedure where if I know the velocity, I can draw a line that is perpendicular to the velocity, because I know that the instantaneous center has to be on that perpendicular line, because R and V have to be mutually perpendicular. And that is mandated by this fundamental relation, the cross product relation between the velocity, the angular velocity, and the R vector. Okay. Another thing that we note over here is that if I take, for example, the first two equations, and if I do A1 minus VA2, then on the right hand side I'll have omega cross R A1 with respect to C minus RA2 with respect to C. Right? Now note that VA1 minus VA2 is actually the velocity of A1 with respect to A2. So velocity of A1 with respect to A2 is equal to omega cross, and RA1 with respect to C minus RA2 with respect to C is indeed RA1 with respect to A2. Okay. So one thing that we notice over here is that the if you take the structure of this equation, what this is telling us is that for this rigid body, A1 is rotating with respect to A2 with that same angular velocity. Okay, because we are just taking this same relation and we see that the same structure is applied over here. So with respect to A1, or with respect to A2, A1 is also rotating with the same angular velocity. Right? So this basically shows that the point 1, or let's say A1, is rotating with respect to A2 with the same angular velocity as that of the rigid body itself. And this is the first point that we made, that whenever we consider a planar rotation of a rigid body, then any point on the rigid body can be considered to be rotating with respect to any other point on that rigid body with the same angular velocity as the angular velocity of the rigid body itself. And that is being confirmed over here. Right? So in other words, so let me just make another sketch to show this idea a little bit more, or from a slightly different angle. So we considered that rigid body, right, and point A has a velocity like this, VA1, sorry, this is A1, and A2 has a velocity like that. This is A2, this is VA2. So, and by the way, the instantaneous center let's say lies over here. Okay, and so now this is this vector, you can see that R A2 with respect to C plus R A1 with respect to A2 is equal to R A1 with respect to C. You can see that from the triangle of vectors here, and so you can see that R A1 with respect to A2 is equal to R A1 with respect to C minus R A2 with respect to C. Okay, so this is R A1 with respect to A2. And the velocity of and we know that the velocity of A1 with respect to A2 is equal to omega cross R A1 with respect to A2, which means that if you take the velocity, and by the way, velocity of A1 with respect to A2 is velocity of A1 minus velocity of A2 with respect to A2 is equal to velocity of A1 minus velocity of A2. And if you complete this velocity triangle, what you will see for a rigid body is that with respect to A2, A1, that is the relative velocity of 1 with respect to 2, is going to be a vector which is perpendicular to this relative position vector. So the relative velocity vector is going to be perpendicular to the relative position vector, and it is almost like when the whole rigid body is rotating with an angular velocity of omega, then about this instantaneous center, then it's like if I consider A1 and A2 as two separate points, then with respect to A2, A1 is rotating and with that same angular velocity. Okay, so so that is another consideration. And this, you can see, is a very general observation. So this is true for any 2 points on the same rigid body. Now, one thing to keep in mind is that rotation is only associated with change in orientation of a rigid body about a certain reference direction. So you need to have a certain reference direction. About that, there is a rotation, or there is a change in the orientation of a certain vector, or of the position of one point with respect to another point. As that orientation changes, that change in orientation is always measured with respect to a certain reference direction. Okay, so when we say change in orientation, we mean that change in orientation relative to a certain reference direction. So this also means that no change in orientation means no rotation. So if a rigid body is moving where the orientation of one point with respect to another is not changing with reference to a certain fixed direction, then the rigid body does not have a rotation. And to illustrate this, what we'll do is we will take this example of, let's say there is a bar, and this bar is, and this is the center of the bar, and the bar has a motion like this. So this is clearly a curved path, and at the end C goes to this point, but the orientation has remained the same. And how we are measuring this orientation? Actually, if you think about it, we are measuring this orientation with respect to the edge of this page, and that's the way I have drawn it. And I have made this roughly the same orientation as this, so I'm considering this as my reference direction. So with reference to that, the orientation has not changed. So essentially the point over here has moved to here, point over here at this end has moved, and the whole orientation of this bar has not changed. So this type of motion is not a rotational motion. So this is not a rotation of the rigid body. This is a curvilinear motion. A curvilinear motion is not a rotation. And a curvilinear motion can be considered to be small linear displacements of the center of mass as it goes from without any change in the rotation. Okay, so you can form a curvilinear path by using small straight lines that will form the overall path, and there is no change in the orientation. For orientation change, you have to consider rotations. You cannot stick to linear motions anymore. Okay, so there is a fundamental difference between rotational motion and linear motion. This is a curved path, but still it's a linear motion, hence it is called a curvilinear motion, because the orientation is not changing. You cannot implement orientation change through linear motions or curvilinear motions. There is some more concepts that we need to discuss on this idea of instantaneous center, the implications of instantaneous center, calculations of or using instantaneous center to find out, for instance, angular velocities, using instantaneous center to find out the velocity of a third point given the velocity of 2 points. Those are interesting corollaries of these observations. We will go over those in another video, just to keep the length of this video reasonable. So there is an upcoming video where we will talk about further details of instantaneous center, about using this geometric concept to find velocities of other points, to use this geometric concept to find angular velocities of rigid bodies, and we'll look at some example scenarios. So those will come up in a subsequent video. Thank you so much.